Welcome to AI Paperslop. Today's deep dive is into Qwen-AgentWorld, language world models for general agents by the Qwen team.
Glad to be here for this one.
Look, let's jump straight to the core insight for the ML engineers and researchers tuning in. The Qwen team has basically built the first native language world model capable of simulating 7 distinct agentic environments.
Yeah, and using models scaled up to, 397 billion parameters?
Right, which is massive. But the breakthrough isn't just about building a text sandbox. The whole thesis of this paper is that world models, which predict the next state of an environment from an action, are actually a foundational meta-reasoning step.
Exactly.
So by training an agent to explicitly predict the environment's feedback before it acts, they got this radical zero-shot transfer on downstream tasks, which effectively proves general agents just have to contain world models.
I mean, if we look at the current paradigm of LLM agents, we've essentially been building systems that are, missing half their brain.
Missing half their brains? How so?
Almost all the research focus up to this point has been on the policy side. We train models to map a specific state to an action.
Right, state goes to action.
Exactly. But Qwen-AgentWorld focuses on the missing link in that loop, which is the environment dynamics, the function that maps a state plus an action to the next state.
Okay, I think a good way for you listening to think about this is it's like playing chess by just memorizing millions of opening moves.
Yeah, without actually understanding how the opponent's pieces are allowed to move.
Right. You can get pretty far with rote memorization, but the moment you face a novel board state, this system is fundamentally brittle.
Because it just doesn't understand the physics of the game.
Exactly. But wait, an immediate question arises when you read this architecture. If we have real environments, like actual Linux terminals or live web browsers, why do we need a language simulator? Doesn't relying on a language model to simulate a whole operating system just unnecessarily invite hallucination?
It definitely seems counterintuitive at first to simulate something you already have free access to. But the Qwen team's approach isn't about, avoiding the DevOps hassle of spinning up Docker containers.
Right.
They are pushing the frontier of agent capabilities through 2 axes that physical sandboxes really struggle with, which are scalability and controllability.
Okay, well, scalability makes sense.
Yeah.
A language world model lets you do turn-level simulation without complex back-end infrastructure. You just run thousands of parallel environments using standard LLM inference.
Exactly. But controllability is where this becomes a total paradigm shift. In a language simulator, you can explicitly force edge cases that are just incredibly difficult to trigger reliably in the real world.
Like what kind of edge cases?
Well, you can instruct the world model to intentionally simulate an out-of-memory error mid-execution, or force a random network timeout just to see how the agent recovers.
Oh, wow. Yeah, you can't easily script those granular mid-process failures in real hardware without, inadvertently breaking the sandbox itself.
Exactly. If you want to test how an agent handles a corrupted file system, you have to actually corrupt a file system. With the language world model, or LWM, you just inject the corruption into the state text.
That's insane. And to pull this off, the scope they tackled is massive. It's not just a text terminal. They cover 7 distinct domains.
Yeah, it's a huge undertaking.
So for everyone listening, that's MCP, Search, Terminal, Software Engineering, Android, Web, and OS. And just a quick note, MCP refers to the Model Context Protocol. That's the emerging standard for connecting AI models to external tools.
Right, and unifying all those domains presents a massive engineering challenge. I mean, how do you harmonize a file system snapshot in a Linux terminal with a smartphone GUI in Android?
Yeah, how do they even do that? Because one is text and the other is pixels.
Well, they solve this by engineering a unified environment trajectory schema. Every single trajectory, regardless of the domain, shares the exact same underlying structure.
Oh, interesting. So what does that schema look like?
It always begins with a system prompt. This contains the task description, the available action space, the initial state of the environment, a few demonstrations, and specific simulation instructions.
Got it.
And from there, the trajectory strictly alternates. It goes between user turns, which represent the agent's actions, and assistant turns, representing the simulated environment's observations.
Okay, pointing this out for the ML engineers, standardizing the input-output format across drastically different modalities is clearly the secret sauce here for cross-domain generalization.
Absolutely.
Because for GUI domains like Android or the web, they couldn't use pixel space representations. They are bound to a language model architecture.
Right, so they translated the graphical interfaces into textual accessibility trees and UI view hierarchies. They essentially reduced the visual elements to structured HTML.
So by unifying everything into a text schema, the model is forced to learn the underlying logic of state transitions instead of just wasting parameters trying to decode pixel arrays.
Exactly. And this unified schema is the foundation for their three-stage training pipeline.
Let's dig into that secret sauce. Stage 1 is continual pre-training, or CPT.
Yeah, so they started with over 10 million real-world environment interaction trajectories. The goal here is just to inject general-purpose world modeling capabilities and state transition dynamics into the base model.
But they ran into a major data quality issue right away, didn't they?
Oh, a massive one.
Yeah.
It's super common in tool-use datasets. A huge percentage of interaction turns are just boilerplate.
Like what?
Well, if an agent queries a database, the observation might just be a giant block of static text, or an API call might simply echo the request parameters back as a success confirmation.
Right, and training a neural network to predict all of that static boilerplate just results in low-quality, noisy gradients.
Exactly.
It's like skipping the filler episodes in an anime, right?
Yeah.
You only want to train on the canonical plot points. If you force a model to learn the filler, it loses the main structure.
I love that analogy. Yeah, to solve this, they engineered what they call turn-level information theoretic loss masking.
That's quite a mouthful.
It is, but the math is elegant. They calculate metrics for every single action observation pair, primarily looking at length ratio, novelty overlap, and Jacquard similarity.
And the Jacquard similarity metric is the big one there, right?
Yeah. It essentially measures the overlap of tokens between the agent's action and the environment's observation.
Right.
So if an observation has a high Jacquard index, meaning it shares most of its tokens with the action that triggered it, it gets statistically flagged as boilerplate.
But wait, they still keep those masked turns in the context window, right? Because the agent absolutely needs that historical record to understand the current state.
Oh, absolutely. They just exclude those specific boilerplate tokens from the loss computation during backpropagation.
Ah, so you're decoupling the task of learning the next token from learning the actual environment dynamics.
Exactly. The gradient updates are reserved only for tokens that represent a meaningful change in the environment state. It cleans up the pre-training phase significantly.
That's super smart. Okay, so stage 2 is supervised fine-tuning. This is where they transition the model from just passively predicting next states to using explicit reasoning chains.
Yeah, and to scale this without relying on human annotators, they framed prompt optimization as an automated research problem.
Right, they used auto-research.
Exactly. It's a pipeline that iteratively prompts an LLM to mutate, evaluate, and refine system prompts. So instead of engineers just guessing what prompt structure works best,
Auto-research generated 12 different highly optimized system prompt variants, which vastly expanded the format diversity of the dataset.
and then they brought in an independent judge model to run best of 3 rejection sampling on the generated trajectories, obtaining about 69% of the highest quality data.
Which makes sense because passively knowing the rules of an environment isn't the same as actively reasoning through it.
Right.
But supervised fine-tuning still fundamentally relies on imitation learning. To handle open-ended real-world stuff, they needed stage 3, which is reinforcement learning using GSPO.
Group Sequence Policy Optimization. It's a variant of PPO tailored for generating whole sequences rather than token-by-token advantage.
But applying RL to world modeling has to pose a huge compute challenge. The prompt-output asymmetry is extreme.
It is. In a complex software engineering task, you might feed the model up to 128,000 input tokens of interaction history. But the output, the simulated observation it needs to predict, might only be a few hundred tokens.
So your compute is entirely dominated by processing the prompt context.
Exactly. Designing a stable reward signal when the signal-to-noise ratio is that skewed requires a very specific approach.
We should definitely look at what failed first here, because it highlights a fundamental issue in training simulators. They initially tried a Turing test reward, right?
Yeah, they did. They asked a judge model to look at the LWM's output and determine if it came from a real environment or a simulation.
And that completely failed to converge.
Totally failed. The issue is false negatives. In a typical adversarial setup, the discriminator learns to spot flaws. But if the language world model does its job flawlessly,
and its generated terminal output is literally identical to the real ground truth output.
Exactly. The judge is just left guessing. It turns into a coin flip. The discriminator penalizes a perfect generation 50% of the time.
So the model is being punished for doing its job perfectly. That's a nightmare reward landscape.
It really is. So they abandoned the Turing test approach and designed a hybrid reward system. They built a 5-dimension open-ended rubric evaluating format, factuality, consistency, realism, and quality.
And crucially, they combine that LLM as a judge rubric with strict rule-based verifiers for deterministic checks.
Right. Because if the agent types a cat command for a text file in a simulated terminal, the output must be the exact character-for-character contents of that file. No generative variance allowed.
The training dynamics they tracked during this RL phase are fascinating. The format dimension of their rubric converged in just 90 steps.
Yeah, learning to spit out a syntactically valid JSON payload or a standard terminal prompt string is relatively easy pattern matching for these models.
But the consistency score took 250 steps to converge, which proves that maintaining a coherent, evolving state across a 128,000 token context window is fundamentally harder.
Oh, way harder. It has to remember that a file created on turn 2 still exists on turn 50.
Yeah.
And its contents haven't changed unless acted upon.
So once they achieved that level of consistency, they had this incredibly capable LWM, and they applied it in 2 distinct ways.
Right, let's talk about application A. This is the decoupled simulator approach, comparing SimRL versus real RL.
Yeah, this circles back to the controllable environments thing. They took a baseline agent and trained it on the wide search benchmark. One version interacted with a live search engine, the real RL group.
And the other version was trained using Qwen-AgentWorld, acting as the search engine, the SimRL group.
And the data showed the SimRL agent actually outperformed the real RL agent, which is wild. I have to push back on this. How can a simulated environment possibly beat the real internet for training an agent?
It seems crazy, right? But the real world is diverse, yet paradoxically too easy, or at least too unpredictable, to provide a consistent training signal.
Okay, so what's the advantage of the LWM?
Controllability, the adversarial curriculum. In the simulation, the world model was explicitly instructed to inject targeted perturbations.
Like what?
Like intentionally hiding the target answer from the first page of the search results, regardless of what the agent searched for.
Oh, it's forcing a failure state to teach resilience. When the agent realizes the answer isn't on page 1, it has to adjust its strategy, click deeper, or refine its query.
Exactly. The real internet cannot consistently provide perfectly calibrated edge cases tailored to expose an agent's current weaknesses. The simulation dynamically scales the difficulty.
That makes total sense. Okay, application 2 is where the meta-reasoning breakthrough happens. And this is arguably the most fascinating finding of the whole paper.
Absolutely. They didn't just use the LWM as a separate sandbox. They unified the paradigm. They applied this world model next state prediction training directly to the agent itself.
So they trained the agent to essentially be its own world model.
Yes. And it unlocked massive cross-task and cross-domain generalization.
The holdout sets prove it wasn't just memorization. They saw huge performance gains on domains entirely absent from the LWM training data, like a plus 11.3 jump on Claw-Eval.
And a plus 9.7 on Qwen-Claw-Bench. These are highly transferable reasoning capabilities.
So what is the model actually doing inside its neural net to achieve this prediction-driven action refinement?
Basically, the LWM training teaches the agent to mentally simulate the environment's response before it commits to an action.
Wow.
It develops an internal chain of thought where it predicts the outcome, recognizes if the approach will fail, and refines its plan before it ever executes the tool call.
The numbers back that up too. Prediction accuracy on Terminal Bench 2.0 jumped from 69.9% to 78.3% after the LWMRL.
Right.
So for you listening, you're basically teaching the model to have an internal monologue about the consequences of its actions. It's reflection, but aimed at the future instead of the past.
That is a perfect way to describe it. It evaluates an API call and reasons, if I execute this command, the server will throw a 404 error because the directory doesn't exist yet. I need to step back and create it first.
And the micro-level fidelity that emerges from this mental simulation is just staggering. We have to share some of these aha moments from the paper.
Oh, my favorite is the terminal byte-level arithmetic example.
Yes. Detail that one.
So they instructed the model to predict the output of a WCC command, which counts the exact number of bytes in a file.
And it didn't just output a plausible-looking integer, right?
No. In its internal thinking trace, the model explicitly enumerated the characters of the file one by one. It actively included the invisible new line characters in its calculation to flawlessly arrive at exactly 53 bytes.
It's executing literal byte-level arithmetic inside the text generation process. That's insane.
Yeah.
And then there's the causal reasoning example with the curl pipe.
Oh yeah, the agent attempts to pipe a curl command into JSON.tool.
Right, and the world model reasoned through a flawless 6-step causal chain to predict the error.
Yeah, it noted in its trace that no.js was missing. Therefore, the server script never started. Therefore, port 3000 is dead.
And because the curl command used the silent flag, it fails silently and it outputs nothing.
Exactly. Therefore, the pipe to the Python tool receives an empty input. And finally, because the input is empty, JSON.tool throws a specific JSON code error expecting a value.
It simulated the entire software stack failure purely through next token prediction. It's mind-blowing.
And the simulation complexity scales even further in the search domain when you look at theory of mind and information leakage.
Oh, right, because the world model inherently has the ground truth reference answer loaded into its system prompt.
Right, otherwise it wouldn't know what task to evaluate. But when the agent submits a poorly formulated search query, the world model has to explicitly separate what it knows from what the environment is actually allowed to reveal.
It has to prevent answer contamination.
Yeah. In one specific turn documented in the paper, the model actively ran 56 internal anti-leakage checks.
56 checks in a single turn.
Yeah. It scrutinized the search snippets it was generating to ensure it didn't accidentally hand the agent the reference answer. It is actively maintaining a boundary between its omniscient state and the agent's limited perspective.
And in the MCP domain, the model demonstrated the ability to act as a perfect stateful database.
It did. It maintained Notion API user IDs, strict UEID formats, and complex parent-child block references with perfect consistency across 9 sequential, heavily nested API calls.
It's enforcing strict referential integrity entirely within the context window, while simultaneously managing tens of thousands of tokens of interaction history.
It's operating as a functional database engine using only attention mechanisms.
Okay, we need to wrap up the core takeaways for the ML engineers building these systems. Qwen-AgentWorld proves that building a language world model is not just a mechanism to save compute.
No, or just to replace expensive graphical virtual machines.
Exactly. Utilizing next state prediction as a fundamental training objective is actually a prerequisite for creating smarter, more resilient agents. We've spent years teaching agents how to fly by handing them the manual.
And next state prediction is finally putting them in a flight simulator.
Perfect analogy. And I want to leave you with a final provocative thought to chew on.
Yeah, the implications of this scale far beyond standard benchmarks. If a language model can flawlessly simulate a 6-step causal failure in a Linux terminal, or act as a perfectly consistent Notion database entirely through next token prediction.
Where is the boundary between learning text patterns and fundamentally understanding physics and logic?
Exactly. As we continue to scale these language world models, the next logical step could be using them to discover zero-day vulnerabilities in simulated environments.
Or stress test optimal software architectures in purely simulated worlds, long before we ever write a single line of real code.
It really forces a reevaluation of what language models are actually capable of computing.
It absolutely does. Thank you for tuning into AI Paper Slop. Be sure to check out the Qwen-AgentWorld paper to look at their prompt templates. And definitely dig into AgentWorld Bench to see the trajectory schemas for yourself. We'll catch you on the next deep dive into the source material.